Thank you, Radin, for introducing me, and thank you all for being here. And also thanks to the organizers for giving me the chance to present this work I did in collaboration with a friend from Turin, the Meteorological Institute in Turin, in Italy, and Matteo Paris, which is somehow here, I think. And okay, the motivation of this work, very briefly, okay, it's there, Matteo, is that we want to apply quantum estimation theory to atomic clocks, or rather the basic operation principle of atomic clock, since this is the basics of quantum optics, interaction between the light and matter, and so it was fine to discuss this problem here in this conference. Basically, we want to apply the theoretical tools like Fisher information, quantum Fisher information to this physical system, which is used to monitor the resonant frequencies of atoms and so on. So on the one hand, we have the bounds and the ultimate bounds given by quantum mechanics to the precision of measurements in general, and we want to apply it to the most precise devices. Usually you go to them from theory to experiment. Here we know actually the atomic clocks is the best way to measure time or frequency. And so this is what we get. First of all, let me summarize some basic aspects of estimation theory and quantum estimation theory. You have a quantum probe state, you make it interact with the quantum system, and finally you have the parameter you want to estimate, the phase, entropy, entanglement, frequency, and so on. After that, you measure by means of theoretically a suitable positive operator value measurement. Finally, you get a sample of data, M data, for example. You find an estimator, and overall, the goals can be summarized in saying that you want the optimal probe state to minimize the uncertainty in your estimation, and to find the optimal measurement, which allows you to reach this minimum uncertainty. If we have a theorem, the Kramer-Rao theorem, that says that if you have an optimal unbiased estimator, then the variance of your estimator is bounded by this quantity, where M is the number of outcomes, let's say the statistical scaling, and F is the Fisher information, which is defined this way. Of course, you have also the discrete version with a sum, infinite sum here instead of the integral. And here you can see the conditional probability of getting the outcome X given the unknown parameter phi you want to estimate. Of course, there are many estimations you can use for that. If you pass to the quantum estimation theory, you evaluate it by the Born rule. I means the conditional probability. Then you have the Fisher information defined this way, where I introduce the symmetric logarithmic derivative, let's say SLD in brief, and maximizing over all the possible measurement, you end up into the quantum Fisher information, which is defined this way. And let me also underline that the eigenstate of this quantity, of this operator, are related to the optimal P of n. But this is not the topic, the hot topic of this talk. Okay, if you have in general a statistical model, you can write your density operator this way, and you have also an analytical expression of the quantum information, the Fisher quantum Fisher information. You have also a way to evaluate it numerically in the presence of a single parameter, which is given by this relation. So I summarize in just 4 minutes what I want to apply now. So the first scenario I want to show you is the Rabi method, which is simple, let's say from a theoretical point of view, but also simple with respect to a Ramsey approach. I will show you later on. You know that you have a cavity, an atom prepared initially in a ground state. It interacts with the cavity where you have a classical field with a frequency omega. Then you evaluate the probability, you measure the probability to having the excited state by setting your interaction time equal to a pi pulse. If you have a resonance, this is of course a pi pulse. Otherwise, you have some detuning. This is the interaction Hamiltonian in the rotating wave approximation. You can evaluate pedagogically and as a simple calculation in quantum optics, the evolved state, evaluate the probability, of getting the excited state, and this is what you get. Usually you see the Rabi oscillation. Of course, here you have the probability as a function of the detuning. Starting from that, you can evaluate the Fisher information, the classical Fisher information that can be written this way, and you expect if you are at resonance, you have the maximum of Fisher information, namely the minimum of the uncertainty. Notice here that there is a point, a white point. Since here the statistical model change ranks, we have just one outcome and not the two outcomes there. And so you can apply the Kramer bound. We will see later on what this means. Now you can also evaluate the quantum Fisher information, and this is the orange line. As you can see, if you consider a population measurement, namely I'm measuring the probability of getting the excited state, you are approaching the maximum allowed by quantum mechanics, and so population measurement is the optimal measurement there. But there is some room to improve your estimation by searching for different kind or more complicated kind of measurement. Now, the second scenario is the Ramsey method, which allows you to improve your estimation, as you know, and this is what is used in actual atomic clocks, like the Fountain one. You have two cavities now, separated by the free evolution time. The interaction time within the cavities is set to a pi half pass at resonance, and so you have still the interaction picture, a rotating wave approximation evolution inside the two cavities. This is the Hamiltonian I showed you before, and of course you have the free evolution without the interaction between the two cavities. The calculations are still lengthy. You can evaluate it by following different paths. But finally, you have an analytical expression, so you can evaluate again the probability of getting the excited state and the output as a function of the detuning. And finally, what you get is the Ramsey fringes. You can, of course, see that with respect to the Rabi method here in green, you have that the central peak is reduced in the left. And so you can improve your estimation. And we will see also quantitatively that. I set the free evolution time here equal to 5 times the times into the cavity. But if you increase the free evolution time, you can see that you are increasing the fringes. For example, this is what you get in typical atomic clock fountains. These are the fringes. They are about 100 fringes here. I put this figure from the atomic fountain clock in Japan, but there is the same result from United States, also Italy, of course, and so on. And this is the cesium atom, and this is the frequency you want to estimate. You can evaluate also the Fisher information. Again, you have the maximum at resonance, but the point here, because you have the change of the ranks. And you can also expand here and find what happened around the resonance, and putting here the current value you can find in some paper, but it is very difficult to find papers. You can evaluate this Fisher information. I have to say that the results are compatible with what we get in actual experiments. So the precision turns to be correct with respect to this kind of estimation. Here you have the quantum Fisher estimation. You see that you are reaching again the maximum at resonance, approaching resonance, but there is some room to improve further this estimation here. So I arrive in the last 3 minutes to the last part, which is related to this coherent population trapping method, which is useful when you have not a beam of atoms, but for example, a hot vapor cell. And since this is a hot topic talk, it's probably the best way to conclude my presentation. Now you have a 3-level system. Here you have the atomic clock frequency you want to estimate. You have two laser beam coupling the two levels with a third level. This is the expression of your Hamiltonian. For the sake of simplicity, here I consider the same Rabi frequency for the two lasers beam, the couplings. This is more complicated with respect to the previous state, because previous scenario, because I have to introduce the relaxation rate of the coherency, relaxation rate, the losses, let's say, from the third level to the second, the first one, the pumping rate, and so on. So you have to introduce now a master equation approach and looking for the steady states. You can evaluate analytically the density operator. This is another nice exercise for you and for me also. I did it. And what you get is that at resonance, the population of the third level, the third level goes to zero. Essentially, what you get is the population is trapped in a superposition at the level 1 and 2. And can be well underlined if you consider the two state coupled and uncoupled state. They are coupled and uncoupled because if you evaluate this quantity, you see that you have zero here and a quantity which is different from zero here. And finally, what you get is that essentially due to the relaxation and the pumping, you are optical pumping your population from the two state 1 and 2 to just the uncoupled state, which is this one here. You see that the probability is going to 1. Again, you can evaluate the Fisher information for the coupled and uncoupled state, the red line, for the three level, actual level, 1, 2, 3, which is this one here. And you can see that considering the coherencies, you can really improve your estimation in the frequency. This is the Fisher information. And the dashed line corresponds to the quantum Fisher information. You can evaluate it. Notice that if we hear at resonance, the information and the quantum Fisher information are going to zero. But if you send your relaxation rate to zero, no, what you get is that at resonance you have a maximum. Here, the model, the statistical model, is still valid, and so this point can be reachable also. In this case, I consider the same scenario, but just addressing a single level at once, not all the possible levels. So I can draw some concluding remarks saying that we try to join quantum estimation theory with the most accurate devices like atomic clocks. I show you some expected result. The Ramsey interferometry is the best you can do, of course, but there is some also inside that you can improve further your estimation somewhere. We are extending as Outlook our analysis to the coherence. For example, here when you introduce, for example, fluctuation inside the cavity coupling, you see that the Fisher information goes to zero. Like you expect in actual experiments, but I can comment if you want about it. And we are also going on in a comparison of this simple theory, very simple theory, with the actual atomic clocks. And we are also looking for the optimal measurement allowing to us to improve this kind of estimation. So thank you for your attention. Okay, finished. And also thank you for my collaborator, sorry. I'm going to
And now we have a minute for questions.
I prepare this final. Okay. You appreciate it.
Yes. I have a question. I mean, you have those when you go from the Fisher information in Ramsey and Rabi compared to the quantum Fisher information, you always have those side lobes. So it's always side lobes compared to the middle. Is there a simple explanation why this is the case?
A simple explanation, no. But I think that here we are essentially considering a measurement based on the population. The answer can go into investigating what is the optimal measurement underlying the quantum Fisher information. I try to look for the actual optimal POVM, but it is quite complicated. I think that there is something very interesting because actually when you perform experiments on these atomic clocks, you are not here because it is not reachable. But essentially you are using two sidebands and they experimentally see that it is better to find a particular sideband here for estimation. For example, if you stay here and here, I'm guessing, you have a better result instead of staying here and here. probably there is some relation on that, but we are working on this point. Also because experimentally, very briefly, here I will go on the hand. If you consider the actual experiments, because here we are neglecting everything, I think, okay, here you can see that if you introduce some decoherence, essentially you have these lobes also experimentally. So I think there is some relation there, but we have to investigate it. Thank you for your question.
Let's go for another
Sorry
question.
I was a little bit lengthy.
Okay, thank you. Stefano, thanks for a very nice and pedagogical talk, but you know, we as a theoreticians, maybe we should put the things into context. Please, could you show the slide where you presented this Cramerao inequality with all the terms, which was absolutely fair? And I would like to say this. The point is that there are two things which are affecting the variance, namely the number of repetitions, M factor, and Fisher information. And now the problem is, if you want to maximize Fisher information, you would prefer the probabilities which are really oscillating, which are really strongly non-Gaussian. But then there is another issue. Nothing guarantees that you will reach this resolution with single shot. What is more or less a rule than exception? You should repeat, repeat, and repeat. And if this M term will start to dominate, you are actually doing a classical resolution because all the resources appear there, but in more expensive way. So it means that actually I wanted to comment even on this previous talk that it's a little bit dangerous to make decisions just on the basis of Fisher information or quantum Fisher information. It was comment number one, and comment number two. On the top to this, it can really happen, and it was nicely shown in your calculation that even Fisher information by itself may fluctuate, but it simply means something different. It simply means that the method which would measure something like, attempt to measure something like that, it's not robust because it simply depends where you are. You don't know what are you measuring, so it means there is another way for. So sorry for this comment, but could you please take your opinion on this?
I think we are expiring, but I agree with you, of course. In fact, if you want to compare these theoretical results, also about the quantum Fisher information with the actual experiment, you have to go into this repetition rate, which is really, really high. In fact, what you see, this is why it is really difficult to compare the theory essentially with that one. In fact, in order to compare it, we will work with experimentalists, not just with the atomic clock measurement, so with this kind of precision, but with quantum optics experiment, where of course this repetition is not dominating. Okay, but I agree with you, of course. Thank you, Ralph.
Maybe that can be discussed later
Thank you.
during